substitution technique, okay? But before we do that, let's review our chain rule in differentiation, okay? Don't write this, you know, already know the answer. If you take a derivative of that thing, it'll turn out to be 4 and then sine cubed x, and the chain rule gives you cosine of x, right? So if you look at this thingy and that thingy, right? You see the relationship here? Oh, by the way, when we have an integral sign without the limits of integration, and mathematicians call it the indefinite integral, it's same thing as antiderivative, okay? Because when we say integral, it really means the Riemann sum, right? This thingy, limit and approaching infinity, sigma, and starting from 1 to infinity, and you know this thingy? This is really what integral is, but that has become this, right? So this thing gives you a number. It's area under the curve kind of thing, right? So that's called the definite integral. But when we drop this limits of integration, then it just means to find the antiderivative between this symbol and that symbol, okay? I think we talked about that already. And then people use the term integrate synonymously to find the antiderivative. So integrate really means this, but when we say integrate this without the limits, it means just find the antiderivative. So antiderivative part of that thingy looks like this thingy. You know what I'm saying? So do you see that answer to this should be then 1/4 of sine to the 4th x? You know what I'm saying? Let's check. If you take a derivative of this, that 4 cancels this and then becomes cubed, and then chain rule, cosine, kind of like this, right? Okay, now, but things are not always that obvious or easy, so I like to give you a more systematic approach to this, okay? And that technique is called integration by substitution. But before we do that, let's review how we learn about the chain rule, okay? So we call this thing sine to the 4th of x, right? And then for the first time we were learning it, we did not know how to take a derivative of this, so we actually made a substitution. Let u be sine of x, okay? Then this thing y now is equal to u to the 4th power, which is much easier. You remember forgetting this? Then, but the trade-off is we don't get dy over dx. This is dy over du. That becomes 4 u to the 3rd power. Now here's the something that got weird. Dy is equal to 4 u to the 3rd power, and then du. I moved that du over here, right? Now what I did back then was then divide both sides by dx. Good. Now let's check. So this dy over dx that we want is 4. What was u? U is this thingy, sine of x. So sine cube of x, and then du over dx. Do we know what du over dx is? Well, we can get it from here. This is cosine of x, and that gets substituted here, right? And this is how we learned how to do chain rule. Few months ago. Good. Now, this technique of substitution is doing all of this exactly backward. So let's start right here from here, sine cubed of x, cosine of x dx. Okay, that's this line, and we are going way back up. So we start with, we have to first notice something is a derivative of something else. Well, cosine of x is a derivative of sine x, isn't it? So we let u to be sine x. That's kind of what we did here, right? And then we calculate du, which is of course cosine of x, and I'll put dx over here, and there's a reason. But now here's a question. Well then, this could be u, because sine of x is the derivative of cosine now, isn't it, with a negative sign, but still. So how do you know which one is which? Sometimes it's obvious, sometimes it's not as obvious, like this case. It could go either way. Here's a rule of thumb. You want to always let U to be more complicated one, like cube here that makes this thing more complicated. You know what I'm saying? This much is easy. So you always want to pick the more complicated one. Watch what happens. So if we make a substitution, this becomes a U cubed, right? This is sine. Now, cosine x dx, all of that is right here, right? So this entire line, so let me make a little note. This is a U part. And then this whole thing, including dx, is the U part. You get it? So all of that now becomes the U. So far, so good? Now, let's look at the new integral. It's so much easier. We find the antiderivative of that thing. Kind of like finding a derivative of this thing, it was easier. You get it? So now we can move on. So U to the fourth power, therefore 1/4 n plus c, 8. Now we have to remember what U was, and U was that thing. We make a substitution back right here. So we have 1/4 of sine to the fourth x and plus c, exactly what we expected. Do we have any questions? Nay? Can I move on to the next example? Yeah, let's do that. So next example is this. U. Okay, what is this, right? Well, how do you like it now? Ah, wait a minute. Which is U and which is du? Should we let U to be sine x like we did before and this is du? Or if this is U, then that's negative of du. Which way is it? How do you know which one to do what? Because they are not, one is not necessarily more complicated now. Okay. I used to get this question a lot. 12 years ago, I used to say this. Well, why don't you try one way? And if it doesn't work out, then it must be the other way. You learn from your mistake. Well, kids got much lazier these days, and they don't like that answer, and they never try it, and they get stuck. So let me screw up for you so you can learn from my mistake, okay? Don't write this down. It's going to blow up. I'm going to let U to be sine x as before, and du to be cosine of x dx, okay? Because that's slightly easier. Let's see what happens. So sine x, u, and then over cosine x, whatever, and then dx, we are forced to do something like this. Good. So that's what dx is. So we have du over. Now, whole idea behind this substitution technique is to make things easier to integrate, right? Did it get easier or prettier? No, not only it's not easier, but we see this is really a change of variable. We change our variable from x to u. Now not only I have u, but I still have x's around. It doesn't disappear. See, all of x must disappear. You know what I'm saying? So this is not the way to do it. You get it? Let's start over. So I'm going to do it here from 0 to pi over 3 of tangent of x dx is equal to from 0 to pi over 3 of sine x over cosine x and dx. Okay, now here, from my experience, I can tell you whenever I have a numerator and denominator, then 95% of the time it's the denominator that's u. Okay, I've seen those rare occasions that actually numerator makes more sense. That's why it's not always, but just when in doubt, start with the denominator, and if that doesn't work, only 5% of the time, then you can try the numerator. How's that? And then du is negative sine of x dx now. So far, so good? Let's see what happens. Now I'm going to make another mistake here intentionally, and it's your job to catch it. So cosine is in the denominator, so we can do this. And then let's look at this. Sine x dx is here, sine x dx. So only thing is the negative sign. If we move over to the other side, it becomes this. So far, so good. Now, those of you who see my mistake, hold your horses a little bit later. Let other people struggle over this. This is one of the most common mistake. Okay, now, then what's the antiderivative here? And only if you're sure we can write this down, because the negative 10-point rule still applies. It is ln, and we are sure, correct? Because 1 over x, 1 over u, 1 over y is the only thing that becomes ln and nothing else. Good. Okay. And then we substitute. Let's see what we got. Ln pi over 3, whatever that is, minus ln, whoops, now we have a problem. What is our problem?
You need to change the limits from x to u.
Yeah, that thing. See, ln 0. This is most common mistake here. That's negative infinity. That's undefined. Right? Wait, but is it then? No, this thing is far, far away from vertical asymptote, which is pi over 2. So this is well-behaved function between these two numbers. Yet we get something that's not so well-behaved. Singularity, if you will. So the problem is right here. So this is not what you want to do, okay? See, when we write it like this, x, this thing matters a lot. X varies from 0 to pi over 3. You get it? Now we change the variable to u. Now u does not vary from 0 to pi over 3. It varies from another number to another number. And what is it? Wow, you know what I'm saying? So what we have to do is, we have to bring u back here. So let me erase this and correct the mistake here. So in order to avoid this common mistake, this is my requirement. I'm taking points if you don't. You have to write x is equal to. You get it? Oh, not there. What am I doing? What am I saying? No. No. Undo. Oh, that I can. You have to say x is equal to 0 to x is equal to pi over 3. This is my requirement, okay? And you write that here as well. Good. Now, and then we have to substitute u back like we did before. So ln, what is u? U is cosine of x. Now we can just write 0 to pi over 3 because x varies from 0 to pi over 3. You get it? Now let's see. That thing is, somebody tell me what's cosine pi over 3? Oh my God, this is calculus BC.
Is it 1/2?
It's 1/2. Okay, somebody else tell me what cosine of 0 is then.
1.
That's 1. Okay, now somebody tell me what ln 1 is.
0.
0. Oh, so this is positive ln 2, obviously. What? Too much algebra? What just happened? You mean ln 1/2? No, you mean negative ln 1/2? Is that the same thing as ln 2? What do you say?
It's 2 to the negative 1 power.
Do you see it? Y'all agree? Okay, good. Now, okay, fine, that worked. But this is so cumbersome. That's a lot of writing. X is equal to, don't you wish there's a simpler way? There is. So let me give you a better alternative, okay? Since I'm teaching with a computer, actually I'm gonna just copy that much and then restart down here. Okay, I'm gonna change the color. Okay, This is our alternative approach. Okay. Instead of saying x is equal to 0 and x is equal to pi over 3, why don't we just change these guys as well? See, we made a change of variable. Instead of x, now we are using u. So the question is, x varies from 0 to pi over 3. What does u vary from what to what? Well, you substitute 0 here, and this is the relationship between u and x now, isn't it? Pay attention, this is very important. Some people never get this. So substitute 0 here, and cosine 0 is 1 here. And then substitute pi over 3 here, then you get 1/2. You get it?
By the way, Mr. Kim, your screen is freezing. Like I can't see the update.
Oh, it's lagging, huh? Yeah.
Yeah.
I see it. Oh yeah, now it's just updated.
Okay, can you explain it again? Because I was kind of lost.
Yeah. Let me do that one more time. You substitute 0 in here because your starting point is when x is 0. So if you substitute 0, then u becomes 1. So your starting point for u, you get it? And then you substitute pi over 3 in here, and then your starting point, ending point for u is 1/2. While x varies from 0 to pi over 3, u will vary from 1 to 1/2. You get it? Yeah, but it's going down. We have a smaller number on top. Yeah, it's okay. We've heard about plumbing professor, and there's no problem with that. Right? In fact, we can actually switch the two and then get rid of this negative sign if you want to, which I'm not gonna do to show you that this is the same thing. Okay? Now, okay, so then as before, this is negative, and then ln of u 1 to 1/2. Oh, by the way, going down is okay because cosine is a decreasing function from 0 to pi over 3, so it's supposed to decrease. You know what I'm saying? This is a natural thing. Now, this will look familiar. You substitute 1/2 minus, that looks weird. One half here minus ln, you substitute 1, and this line looks exactly same as before now, doesn't it? So we end up with ln 2. You get it? And we'll go back to x. Gives you the same answer. Question?
Yes. I'm just wondering, like, what's a good part of this, or does it change anything, or is it more convenient sometimes?
It's a lot more convenient, many times.
Okay.
I will accept it either way. This is perfectly okay, but you have to remember to write x is equal to and x is equal to. Okay, that's the only thing.
Oh, you have to.
Yeah, you have
Even
to.
at the integral part, you still have to. Okay.
Yeah, here and here. Whenever you have a mismatching value limits with a variable, then you have to write it. This is my requirement. I take off a point to remind you. So more the reason not to use this technique. Some teachers prefer this. I don't. Okay, it's a lot less writing. This line right here is exactly the same as this line right here now, is it?
Yeah.
Okay. Now, terminology. This is known as the official is change of variable. More professors will say change of variable in integration. But our book calls it substitution, integration by substitution, because we make a substitution right here. You get it? And regretfully, most teachers, I didn't come up with this name, so don't shoot the messenger. They call it U substitution because we are using U as opposed to trig sub that you're going to learn later in this chapter. Yes, as people throw that term around, U sub. That means this substitution, change of variable. You get it? Any other questions?
So we don't have to show the work for like substituting the limits, right?
No, if you change it to the right one, and I will assume you know what you're doing. antiderivative of secant x. This is what not to do. Don't write this down because this is how you get negative 10 points. The secant, of course, is this, right? Oh, 1 over cosine. That must be then ln, right? Do you even see what's wrong with this? Because I see this so many times. Right. Let's just take a derivative of this, and then we better get that, right? If you take a derivative of this thingy, I'm just going to write it out and do it. Derivative of ln cosine of x, of course, is this, right? And then chain rule. Derivative of inside thingy. This always happens. You know what I'm saying? So this gives you tangent. So not even like this is like, no, this is negative 10 points, okay? Don't do it. Don't do it. You've been warned so many times. Even on secure browser, I will still give you negative 10, okay? So let's not ever do that. 1 over x is the only thing that becomes ln, okay? Now, then, what are we supposed to do? So we have secant x dx. Now, the hint says multiply that in. Can we just multiply that and claim it's the same expression? Yeah, because we are inserting 1. You can always multiply 1 and not change it. That's called the identity, right? Multiplicative identity. Have you heard that kind of terms before? What's the additive identity? A plus 0 is still A. That's additive identity. A times 1 is still A. That's a multiplicative identity. You know what I'm saying? So you can add 0 and you can multiply 1 and then you get exactly the same thing. Okay. So we multiply that 1 and then let's see what happens. So the denominator becomes, of course, secant x plus tangent x. Numerator, secant x here becomes secant squared x plus secant x times tangent x dx. So far so good? Are we good? Okay, then what? Do you see it? Okay, here's a hint. We are still doing u substitution. Which is u? And do you see a du? Do you see 1 and the derivative of that one? And I told you yesterday, when in doubt, 95% of the time, go with Colin.
The denominator.
Denominator. Let's try. It may happen anyway, right? So let's see, because it looks unlikely. U, really? Du. What is du? Derivative of secant is secant x tangent x, right? And derivative of tangent x is secant squared x, the whole thing e times dx. Don't forget the dx. Wait a minute. Is that thing the entire numerator and dx? Yeah. Magic. Oh, no, it's logic. Instead of writing 1 over u, if I write it like that, does it bother you? It's really the same thing, right? It's really the same thing as having du here, but this happens all the time, so I just want to show it to you so you don't get confused over it later. Okay, so this is ln, and we are sure. Good. Say yes. Now,
Yes.
then we have to remember what u was, and u was that this thingy, right? So we substitute that back. Oh my God, that is ugly, right? I know this is quite ugly antiderivative. But this is more of a trick, okay? If you've done it a few times, then you know this. Not that we memorize it, but like we can do it in our head, kind of thing. And many teachers will just tell you to memorize it, but no, you know how I feel about memorizing stuff in math, right? It's like, it only takes 4 lines, and you can just recall all of that in your head. Any questions? Okay, then. Number 4. They actually tell you what u is. I wish they don't, but we can see. Do we see a derivative of this somewhere? Yeah, right there. It's not exactly the derivative, but we can tweak it. You know what I mean? So we'll start right here. So if our u is equal to 1 minus r cubed, and then you have to think about my motivation. If this is u, number 1, do I have a du? And du looks like this. Negative 3r squared dr. You know what I'm saying? So it's not exactly but 3. Yeah, I have some du. The other thing is, once I do that, do all of this disappear, and does it make my thingy look prettier? Okay. For beginners, let me give you this idea. See, I see 9r squared dr, right? So if I try to have 9r squared dr, then do you see this is negative 3 du? You know what I'm saying? That's how we adjust it. 9r squared dr is equivalent to negative 3 du. You know what I'm saying? Okay, so let's see what this thing becomes. So I have negative 3 here, and then u to the negative 1/2 power a. Do you agree? Wait, too much algebra? What just happened? Do you guys agree? The whole reason we make this substitution is that integration is easier. You know what I'm saying? Because this is 1/2 power in the denominator, so negative 1/2 power, and I want all of this to disappear, and this is how you make it disappear. So once you do that, then it's easy, and watch this. U to the 1/2, I do this first, right? So I have to compensate it by doing this. You know what I'm saying? And then quick check, derivative. If I differentiate this, 1/2 comes down and it becomes to negative 3, and then subtract 1. Yeah, that's right. Then all we have to do is remember what that u was, which is 1 minus r cubed, so negative 6, and I'll write it as square root 1 minus, and you don't have to write it as square root. They look identical to me. How about that? Good? Are we good? Okay, then let's do number 5. Number 5, we can do it in 2 different ways, okay? Let's see. So if we let u to be cosine, cotangent to theta, then du here is, what's the derivative of cotangent? Negative cosecant square, and then there's a chain rules at 2. You with me? You with me? So now, having said that, this integral then, cosecant square, let me write it in different order so that it's easier to see. So I'm going to write cotangent to theta, and then cosecant square to theta, and then d theta. Let's take a look at this. This thing is u, right? And then almost all of this is du now, isn't it? Except we have negative 2, so we can bring that negative 2 to the other side and put negative 1/2 in front. 8. So what we are going to have is negative 1/2, and this becomes u and then du. How about that? Ain't that nice? Very good. Now then, of course, integrate. So we have u squared, therefore adjust this thing to 1/4 plus c. Now remember what u was, which is cotangent to theta. So this thing becomes negative 1/4 cotangent square to theta plus c. How about that? Y'all with me? Questions? Okay, then I'm going to push this down a little bit. Let's try this with u being cosecant to theta. Most people will not do it that way, but it's possible. Watch. So du happens to be, what's the derivative of cosecant? Negative cosecant and cotangent, eh? And then chain rule that 2. Bang. Good. Now, then this given integral, let me write it this way so you can recognize it. I'm going to write cosecant to theta and cosecant to theta, cotangent to theta, Now, why the hell would you want to do that? Watch this. This thing is u, and all of that is du then, isn't it? You get it? So all of this, almost du, because that much is right here. So once again, 1/2 to the other side. So this thing will change to negative 1/2, and then u, and the other part is du. Any questions so far? Okay, then we integrate, almost recycle our work. So this is negative 1/4 u squared plus c. But this time, my u is cosecant to theta. Right? So far so good. Now we have a conflicting answer, and then wow, I thought math is consistent and there's only one answer, right? What is this? Are they really different or not? What's the difference between cosecant square and cotangent square? That difference is literally 1. What? Do you remember this? Cosecant square to theta is equal to 1 plus, you know, this thingy like this. Remember that? Well, having said that, then we could have easily done it this way then. See, I told you the difference between the two is literally 1. What? So you remember these things have constants, right? So this c is not same as this c. Maybe it's better if I use different constant here then. D. You get it? C and D in this case differ by 1/4 because there's a 1/4 here. Now graphically, let's take a look because I have graphed both. This is the graph of cosecant square. And this is graph of cotangent square. You see that's just a vertical translation of 1 unit. You know what I'm saying? See, when we say plus c at the end of the integration, there are technically infinitely many answers. This could be 1, 2, 3, 4, 5, 6, any number, any constant. You get it? So there are infinitely many. This is a general solution of differential equation, if you will. So these two are still kind of the same thing. You know what I'm saying? As long as they are only differ by constant, we consider that as the same answer in calculus. How about that? Are we good? So that's the mystery between two conflicting answers. They are really not. We have to remember our identity. Okay, I'm gonna box this thing. Okay, now, then we're going to do this one. This one looks relatively easy after all that. So what should be our u? That thingy, of course, right? So our u in this case should be 2x plus 1. Then my du, of course, is 2 dx. You get it? Du over dx is equal to 2 is what that says. So far so good. So let's see how this thing transforms then. So integral of this is u cubed in the denominator, which I will write like that. And dx is du over 2, isn't it? Let's put that 2 on the other side. So adjust it by half like this and du. Are we good so far? Now we have to change the limits of integration. When x varies from 0 to 1/2, u will vary. Substitute 0 here, so u will start with 1. See, when x is 0, u is equal to 1. You get it? This is where we get it. This is a relationship between u and x. And when x is equal to 1/2, put 1/2 here, then we get 2. Are we good? Now, after this, in definite integral, we never come back to x. We just substitute this. So that is equal to now u to the -2, therefore -1/2, right? Combine it with this. You with me? And then 1 to 2. So far so good? Okay, so this is -1/4 of, put 2 in, is it 1/4? -1/8? Say yes. So this is 3/4 times 1/4. So we have 3/16. How about that? Good. Okay, any questions?